What's up, guys? Are you ready to cram some identities? Maybe you have a test, a quiz coming up, or maybe you just forgot about trigonometric identities and you need a little quick refresher. Well, in this video, that's exactly what we are going to do. We're going to go through the basic identities, remembering how to simplify them, how to verify them, solve using identities, and also be able to evaluate using your double angle and sum and difference identities. So if you're ready, let's go ahead and get started. So the first thing we want to remember is our basic identities. Now, I don't really have my students memorize these because I'm like, you need to know these identities. So if I had tangent of theta, remember that's equal to the sine of theta over cosine of theta. Cotangent of theta is going to equal to a cosine of theta over sine of theta. And basically we should be using these enough to remember these. And then we're going to go on to the reciprocal identities, which again should be fairly used to based on just our knowledge of our sine, cosine, and tangent. So I could have the sine of theta, remember, is equal to the reciprocal of 1 over a cosecant of theta. We have the cosine of theta is equal to 1 over a secant of theta. And we have the tangent of theta is equal to a 1 over the cotangent of theta. And again, this is important because a lot of times we'll get mixed up. Should we use tangent as sine over theta or tangent as 1 over cotangent? But again, we'll go back and review all of that for you. Now, since sine of theta is equal to 1 over cosecant of theta, well, guess what? That means cosecant of theta is equal to a 1 over sine of theta. And we can do the exact same thing for secant of theta. That's 1 over a cosine of theta. And then also we have the cotangent of theta is equal to 1 over the tangent of theta. Now, the next two identities that I think are really important to recognize, but they don't really come up as often, are going to be your even odd identities as well as your cofunction identities. So remember, one of the mistakes students make when we're looking at these, the differences here is tangent of theta is sine of theta over cosine of theta. And here tangent of theta is 1 over cotangent of theta. Sometimes it gets hard to understand which one is which, but again, that's what we'll go ahead and work on in this video. Now, these two functions get often missed by students because we don't use them a lot, but I think it's really kind of important to recognize two things. For me, the easiest way to recognize these is just to kind of think about the graphs. So if you think about the sine and cosine graph, so here is going to be the sine graph, and here is going to be an example of the cosine graph. Now, the way I like to think about these is looking at your graph like sine of theta and cosine of theta. So what's important about this is on the sine graph, if this negative theta, what that's actually doing is that's finding a value that is going to be on the other side. If I have a value of theta and I have a value of negative theta, well, it's important to recognize that this graph is going to go down. So the y coordinate, the value is not going to be the same. That's why the sine of a negative angle is equal to a negative sine of theta, right? You can see that's negative. Whereas the cosine graph, when you're looking at a theta here, that's positive. And when you look at negative theta, that's also going to be positive. So that's why the cosine of a negative angle is still equal to the positive value of cosine. Because the thing is, cosine and secant are both what we call even functions, meaning they're reflective about the y-axis. Whereas the sine, tangent, cosecant, and cotangent are all odd functions. Therefore, they're reflected about the origin. Now, as far as the cofunction identities go, you can just think about those as like transformations, right? When I have pi halves minus x, what that's doing is you're actually shifting the graph. And the way that I recognize these is notice that cosine can only look like sine and sine can only look like cosine. That is why we call them cofunctions of each other. The same thing works for tangent and cotangent. If you look at the graphs of cotangent and tangent, they're only going to ever look like each other, right? There's no transformations that I can do to the cotangent that's going to ever make it look like sine. So therefore, cotangent and tangent are going to be cofunctions of each other. And the same thing for the cosecant and secant. So it's just important whenever you see that pi halves minus x, or you see 90 degrees minus theta, that you think about these identities. They don't come up often. It's really important to recognize the relationships of their graphs so you can quickly remember what the identity is as well as then apply them. So now let's go and just take a look at like a common mistake that students will make, just on simplifying. Remember, when we're typically looking to simplify, what we're trying to do is we're trying to get this down to one single function or number. So if I have sine of theta times cotangent theta, what a lot of students will try to do is they'll use the wrong identities. And what I mean by that is they will say, all right, well, sine of theta times, let's see, that's going to be a 1 over a tangent of theta. And then they'll say, oh crap, well, that doesn't help me simplify, right? So that's not going to work. So then they say, well, what about if I do the sine? I'll do 1 over cosecant of theta times cotangent of theta. And that one doesn't work either. So then they say, well, let's go ahead and do both. And so 1 over cosecant of theta times 1 over tangent of theta. And again, you can see, even though these are all true, none of these help simplify out. Remember guys, our goal is to get this eliminated. We want to have the same term in the numerator as well as the same term in the denominator. So in this example, what I'm simply actually going to want to do is I'm going to keep sine exactly the same, but I recognize that the quotient identity for cotangent, that's equal to a cosine of theta all over a sine of theta. Now we recognize that sine of theta is in the numerator and this sine of theta is in the denominator. Since they're exactly the same, they're going to divide to 1, which is just going to leave us with a cosine of theta. So when we're trying to simplify, try to get those same terms in the numerator as well as the same terms in the denominator. And again, sometimes choosing the identities might be obvious. Sometimes it becomes a little bit more difficult. It just comes with a little bit of practice of looking ahead and seeing where you're going to have the same term in the numerator as well as the same term in the denominator. Now in this example, you can see I have multiple different functions, and I also recognize that I have negative theta. So immediately my brain goes to knowing my even odd identities. I also see that I have a pi halves minus theta. So therefore that goes into using my cofunction identities. Remember, cosine and secant are our even functions. So the secant of a negative angle is just going to be equal to a secant of theta. Sine is an odd function. That's going to be equal to a negative sine of theta. And then here we have the cotangent of pi halves minus theta. Now again, what is the cofunction? What other graph looks like cotangent? That's the way I like to sometimes rethink about the cofunction identity, is just think about what graph looks like cotangent. And again, that answer is tangent. So therefore I have a tangent of theta. Now it's important to see that I use parentheses here because I didn't want to confuse this with a subtraction problem, right? This is still multiplication. So to simplify this, I'm going to go ahead and multiply my numerator to try to get it down to one expression. So when I do that, I have a 1 over a cosine of theta times a negative sine of theta. Again, remember that's in the numerator, all over a tangent of theta. Now, hopefully you recognize here, this can be multiplied just to give me a negative sine of theta over cosine of theta divided by a tangent of theta. And what do we recognize about sine of theta over cosine of theta? Well, that's equal to a tangent of theta. So now I basically have a negative tangent of theta all over a tangent of theta, which is now going to be equal to a negative 1. So when we're looking to simplifying, we're either looking for having a function as our simplified answer, or we're looking for a number. And again, it all depends on what the directions are of the problem that you're looking to solve. Now in this example, they're just asking us to multiply. We're not necessarily looking to reduce this down to a single trigonometric function or a number, but that could be the case. But the main idea is just making sure that we can apply the operation of multiplication and then simplify as available. When I recognize whenever I have a function outside parentheses, I need to make sure I multiply every single term inside the parentheses that's separated by addition or subtraction. That's the good old distributive property. It works for numbers, works for variables, and it works for our trigonometric functions. So when I do that, what I'm going to have is a cosecant of theta times a sine of theta, and then minus a cosecant of theta times a cosecant of theta. Now again, you don't need to maybe write down the second line, but I think it's always helpful to show our work, especially just to make sure we're not making any mistakes. What I recognize here is these are reciprocals of each other. And just remember, anything multiplied by reciprocal is always 1. You could write cosecant as 1 over sine, or write sine as 1 over cosecant, but really go through all those steps, right? This is going to be multiplied to 1. And then over here, a cosecant times a cosecant is going to be a cosecant squared, which I will want to write as a cosecant squared of theta. Now, the next thing I recognize here is whenever we're dealing with squared expressions, that's going to remind me of my Pythagorean identities, which we have not covered yet. So let's go ahead and write them out. Okay, so if you remember the Pythagorean identities like a squared plus b squared equals c squared, and you can see that exact same relationship is playing out here. Now, once you know this identity, all you need to do is either divide by sine times everything or cosine by everything to get these other two identities. This might not look like a Pythagorean identity to you as it's currently written. However, if you recognize if I subtract a cosecant squared of theta on both sides, I get a 1 minus a cosecant squared of theta plus a cotangent squared of theta equals 0. And then if I subtract a cotangent squared of theta on both sides, you can see now I'm going to have a 1 minus a cosecant squared of theta is equal to a negative cotangent squared of theta. Just remember with these Pythagorean identities, you can manipulate them to get exactly what you want. So we can actually simplify this expression to a negative cotangent squared of theta. All right, in this next example, we have cosine of theta minus secant of theta. And basically what we want to do is just try to apply the operation by subtracting these. Now, these are not like terms. So what we're going to want to do is actually rewrite these using our identities. Therefore, we can rewrite them as fractions. So if you notice here, if I rewrite cosine minus secant as a 1 over cosine of theta, What that does now is that creates this to be a fraction. Now remember, when we are subtracting fractions, all we have to do is get common denominators. So right now I have a 1 and a cosine of theta as my denominators. So if I multiply by cosine of theta over a cosine of theta, now what I'll have is a cosine squared of theta minus 1 all over a cosine of theta. Now it's important again to, whenever we see a trigonometric function squared, is to think of your Pythagorean identities. So going back to this list I have here, sine squared of theta plus cosine squared of theta equals 1. Now again, what I'm looking for is a cosine squared of theta minus 1. So if I subtract a 1 and then subtract a sine squared over to the other side, I can go ahead and rewrite this as a negative sine squared of theta all over a cosine of theta. That could be a typical answer, but a lot of times when we are taking a test and a multiple choice, it might be rewritten in a different format. Remember, we can manipulate these using our identities. So sometimes, let's say the answer is not written as a fraction. So what I recognize here with this sine squared of theta is I can rewrite this as a negative sine of theta times a sine of theta all over a cosine of theta. Now I can go ahead and group these because everything is separated by multiplication. And what that's going to give me now is a negative sine of theta times a tangent of theta. So that could also be another answer. So whenever you're doing a test and you're simplifying or applying operations, if you don't get the right answer, that doesn't mean you necessarily did something wrong. Look to ways that you could further simplify or apply an identity to get exactly what you were looking for. In this next example, rather than actually trying to combine these, we're looking to actually simplify these by factoring them or to rewrite this as a product. So what I notice is they both share a tangent of theta. So what I can do is I can factor out that tangent of theta. When doing that, that's going to leave me with a 1 plus a tangent squared of theta. And again, thinking about this tangent squared, I say, hey, let me go and check my Pythagorean identities. And checking my Pythagorean identities, you can see a 1 plus tangent squared is equal to a secant squared of theta. So therefore, I can rewrite this tangent of theta times a secant squared of theta. And so if the problem was saying to factor this expression, remember you can factor out using common terms or you can factor out trinomials. But the important thing with all of the problems that I've done today, whenever you're applying an operation with functions, it's the same operations we've been applying with variables as well with numbers. So if you get stuck, use some x's and some y's, use some 2 and some 3's, whatever is going to help you to understand the process a little bit easier. Now, the next thing we want to work on is actually verifying identities. Now, the cool thing about verifying identities is it's really just an extension off of what we just did for simplifying. Remember simplifying when you're trying to condense the expression down to a single function or number? Well, with verifying identities, basically all we want to do is simplify one side of an equation to make it look exactly like the other side. So it doesn't necessarily always have to be one function or number, but what we're going to have to do is apply operations like we just practiced, as well as apply our identities to further simplify or rewrite one side of an equation so it looks exactly like the other equation. Here are some of my favorite tips that we can use for verifying identities. Okay, so when you want to pick the hardest side first, basically what you want to do is pick the side that looks the most complicated. And the reason why we want to do that is because it's a lot easier to simplify something like by combining fractions rather than taking a single function or number and rewriting it as two fractions added or subtracted. If it looks like both sides are going to be kind of complicated, then just go ahead and pick a side. And if it doesn't work out, you can always go back and try the other side. But basically you want to pick the side that has operations like addition or subtraction, multiplication or factoring, maybe a rational expression that you could rationalize to the denominator. Look for something where you can apply operations, or look for the side that you can apply your identities like the reciprocal identity, the quotient identity, the Pythagorean identity, the even odd identity, the cofunction identity. Look for ways you can simplify the expression like we did previously in this video. And then just go ahead and simplify. Sometimes you're going to get it exactly to look like the other side, and sometimes you're not. That's why the last step is the most important, is to try, and try again. With more practice, you're going to get much better at doing this, but the main thing is just to pick something and then work with it. See if that identity works. See if that operation is the right operation. And again, remember, we can continually manipulate our expressions using different identities to get the result that exactly what we're looking for. So since we already covered a lot of simplifying by adding, subtracting, multiplying, and factoring, let's go ahead and practice one with rationalizing the denominator to make one side look like the other side. All right, so let's go and look at this example. Since we've already kind of covered adding and subtracting fractions, multiplying and factoring, let's go and work on one where rationalizing is going to be an operation that we can apply. So in this example, typically I would choose the left side first. And the reason being is because this is rational and this is not. Usually it's easier to simplify a rational expression than it is to create one. But that's not always the case because we'll actually be able to work on both sides here. Whenever I see a binomial like a 1 minus sine of theta, I want to think about rationalizing by multiplying by the conjugate. So in this case, the conjugate of 1 minus sine of theta is a 1 plus a sine of theta. So what I'm going to do is I'm going to multiply by 1 plus a sine of theta on the top and as well as on the bottom. Now, one kind of tidbit is don't always just jump to simplifying this. I'm going to leave this as a 1 plus a sine of theta times a cosine of theta. Because again, you don't know when you need to simplify things and when not. Now, a 1 plus sine of theta times a 1 minus sine of theta, that's a difference of two squares. That's what's so nice about rationalize the denominator here. So that's going to give me a 1 minus a sine squared of theta. It's important for us to recognize here is this is still equal to the right-hand side, but I'm not going to write anything on the right-hand side because again, our whole goal here is to make the left side look exactly like the right-hand side. I recognize the Pythagorean identity here, 1 minus sine squared of theta is going to equal to a cosine squared. So therefore, I can rewrite this as a 1 plus a sine squared of theta divided by a cosine of theta divided by a cosine squared of theta. Well, since everything's separated by multiplication, I can divide out the cosines, but I'm still going to have an extra cosine left over here. So what I'll have here is a 1 plus a sine of theta divided by a cosine of theta. And then I can divide this cosine into both of these terms, which is now going to leave me with a 1 over a cosine of theta plus a sine of theta over a cosine of theta. We can simplify this into a secant of theta plus a tangent of theta using my identities. Now, let's say you actually decided that, well, I didn't want to work on the left-hand side. I actually was planning on working on the right-hand side. And sometimes that's not a bad case because if you see a separation of two fractions and you see this written as one fraction, sometimes it's a lot easier to think about just combining these by adding them. So if you're going to work on the right-hand side, it could look something like this. I would recognize these are not in terms of sines and cosines. So what I do, I combine them so they're in terms of sines and cosines. So I write that as 1 over cosine of theta, and then this one would be sine of theta over a cosine of theta. Now I can go ahead and combine them. So that'd be a 1 plus a sine of theta all over a cosine of theta. Now again, a lot of students will get stuck here, but just like we rationalized over here in the denominator, here we can rationalize the numerator. All you're simply going to do is multiply by the conjugate. So I'd multiply by 1 minus sine of theta on the top and on the bottom. Now again, what is this going to produce? 1 minus sine squared of theta all over a cosine of theta times a 1 minus a sine of theta. Now again, we recognize from the last example, 1 minus sine squared of theta, that is going to equal a cosine squared of theta all over a cosine of theta times a 1 minus a sine of theta. And then here, we could actually go ahead and divide these out. And guess what? It's about the same number of steps to get the exact same answer. Now, that's not always the case. A lot of times working on one side is going to be far easier and far faster than working on the other side. But I just wanted to highlight that how you can approach these problems where don't always feel like if you're going to make the right choice using left and right, some sides are going to be more difficult and you might get stuck. So go ahead and flip over to the other side. But notice when I worked on the left side, I stayed on the left-hand side. When I worked on the right-hand side, I stayed on the right-hand side. But rationalizing the denominator is a powerful operation that you can apply that allows us to create our Pythagorean identities to further help simplify a side and to verify the identity. So again, just the main thing with verify identities, we want to make sure one side is equal to the other side. All right, the next thing I want to talk about is solving equations. So just remember when we're solving equations, basically two restrictions we're usually looking for our solution is one, which is on 0 to 2 pi, which is basically going to be restricted to the unit circle. And then the other one is going to be all solutions, which is basically going to mean continuously repetitions circling around the unit circle. So there's definitely some different ways to approach how we're going to be solving each and every one, especially when we have multiple angles or multiple functions that we're dealing with the equation. So let's go and take a look at a couple examples here. First one, I'll just go ahead and solve on between the interval of 0 to 2 pi. And that one is going to be a 2, let's say sine of theta minus 1 equals 0. So the main thing, like the number one thing you need to do is isolate your trigonometric function. So in this one, I'm going to add a 1 to both sides. That'll give me a 2 sine of theta is equal to 1. Then I will divide a 2 on both sides. And I'm going to get a sine of theta is equal to 1/2. Now, if I'm looking for only the interval on 0 to 2 pi, basically what I'm doing is now I'm just looking for when is sine or when is the y coordinate going to equal 1/2. So pulling up my unit circle here, and hopefully you have these kind of angles memorized that you recognize these coordinate points have a y coordinate of 1/2. Now we just need to know, well, what are these angles? So we have this angle and that angle. And we can just rewrite this as a solution set. And that's angles are going to be pi over 6, which is the first one, and a 5 pi over 6. So on the unit circle, these are the only two solutions where the y coordinate is equal to a positive 1/2, right? The sine of what angle equals 1/2. That's what we're looking for. What are those angles? But again, it's only the angles between 0 and 2 pi. That's why the restrictions are so important. It can't be over here because the y coordinate would be a negative 1/2. So what about when I have a double angle, like 2 cosine of 2 theta minus 1 equals 0? Now in this case, we're going to do the exact same thing. We're going to add a 1 to both sides, and then I'll get a 2 cosine of 2 theta equals 1, and I'll divide by 2, and therefore I'm left with a cosine of 2 theta is equal to 1/2. Rather than finding the intervals on 0 to 2 pi, we now want to find all of the solutions. So we want to find each and every one of these answers. So what we're going to do is I'm actually going to find the answers on the unit circle first to help me go ahead and find all of the solutions. So the first thing we're going to want to do is actually draw the unit circle here. And now I want to figure out when is cosine of 2 theta equal to 1/2. So again, remember cosine represents the x coordinate where sine represented the y coordinate. And cosine is going to be positive 1/2 here at this angle and at this angle. Right? Because, because this angle is 1/2 comma square root of 3 over 2. And this one is going to be positive 1/2 negative square root of 3 over 2. Now again, you need to know your angles here. So this one is going to be a pi over 3. And this angle is going to be a 5 pi over 3. Now again, this is for solving for 2 theta, not just theta. And also remember, we're not trying to find on the interval of the unit circle. We're trying to find all of the solutions. So it's important to recognize that, let's just say I'm traveling around the unit circle. If I have pi over 3, I'm going to have to add 2 pi to go all the way around the circle as well. But if I keep on adding 2 pi, every single I add 2 pi, I'm going to keep on landing on this angle, which is going to be a solution. So I could add 2 pi or I could subtract 2 pi going in the opposite direction. But no matter what, as long as I add or subtract 2 pi, I'm going to keep on getting a solution for this equation. So therefore I can say 2 theta is equal to a pi over 3, which is the solution on the unit circle, plus a 2 pi n. And the reason why n is because I can keep on adding 2 pi infinite many times or subtracting 2 pi infinite many times. So n is going to be a real integer, positive or negative. I also have a solution at 5 pi over 3. And again, I can keep on adding 2 pi to these to keep on getting more solutions. But again, that's for this equation is when 2 theta is equal to a 5 pi over 3 plus 2 pi n. Now again, remember our equation is solving for theta, not for 2 theta. Right? So what we need to simply do is now just divide by 2 on both sides. Now, the reason why we couldn't do this at the beginning is because this was not being applied to the function. This is inside of the function. So we use our inverse operations to isolate it to this equation. We find our solutions using the unit circle. And then when we're looking for all solutions, we're just looking for what interval can we add or subtract to continue getting solutions. In this case, we had to keep on adding 2 pi n to our solutions. Therefore, I get a final answer of theta equals a pi over 6 plus pi n. And over here, I get theta equals a 5 pi over 6 plus pi n. Now, in this next example, you can see that I have multiple trigonometric functions. So when you have multiple trigonometric functions, you can't use your inverse operations like we did before. What you're going to want to do is either simplify them or look to factoring. And in this case, you can see that they both share a tangent of theta. So what I'm going to do is I'm going to factor out a tangent of theta. When I do that, I get a sine of theta minus 1 is equal to 0. The reason why factoring is so important is because now I can apply the zero product property. So I can say tangent of theta equals 0. And here, a sine of theta minus 1 is equal to 0. So therefore, I can get a sine of theta equals 1. Now, in this case, what I'm going to do is I'm going to solve this between 0 and 2 pi, as well as I'm going to find all the solutions for b between negative infinity to infinity. So you can see the difference between these two solutions. Let's go ahead and find the first one, which is on the unit circle. So when is tangent of theta equal to 0? Now remember, for sine represented the y coordinate, cosine represented the x coordinate. Tangent represents the y over the x. So it's really important for you to recognize, then again, these points, 1, 0, 0, 1, negative 1, 0, and 0, negative 1. Okay, so when is the y coordinate over the x coordinate going to equal to 0? We cannot divide by 0. So for this angle and this angle, y over x is going to be undefined. So the only two solutions here that we have is going to be a 0 and going to be at pi, which is going to be at this angle, which is 0, and then this angle, which is going to be at pi. And 0 is included. We're going to use 0, not 2 pi, because you can see 0 is included with the bracket, whereas 2 pi is not included with the parentheses. Now let's go and look at when is sine of theta equal to 1. Well, sine represents the y coordinate is only going to equal to 1 here at this angle, which is pi half. So the solutions to this equation is going to be 0, pi, and pi halves on the interval of 0 plus 2 pi. Now let's go and take a look at, what about if I said all solutions? So the one thing I want you to recognize here is, do you notice what is the distance between this angle and this angle? Well, it looks like the distance is pi. Like if I take 0, I add pi to it, I get to this answer, which is pi, right? If I add pi again, I get to 2 pi. It's also going to be a solution on the full interval. And if you keep on adding pi between these two answers, you're going to always get an answer. So therefore, I can say theta equals a pi n, where again, n can represent any number. It can be -1, it could be -2, it could be +5, it could be 0. No matter what number n is, it's always going to give me one of these solutions, right? Either on this axis, or I'm sorry, it's either going to give me the solutions on this axis. However, for pi halves, the only way for me to get to another solution is for me to add another 2 pi. So therefore, this is going to be theta equals a pi halves plus a 2 pi n. And that's basically what you need to do for solving your trigonometric functions. Make sure you know your interval. Make sure if you only have one function, use inverse operations to simplify. If you have more than one function, then look to factoring or to simplify it down. But it's always really important to use the unit circle to recognize when your equation is going to be true. And sometimes actually also looking at a graphical approach can be helpful to make sure you have the number of solutions that you possibly need. Next one I want to talk about is the sum and difference formulas. Now for the sum and difference formulas, we can solve equations like we just did. We can verify identities like we did. We can simplify expressions as well as evaluate our trigonometric functions. So it's really important to make sure that you recognize these and be able to apply the formulas. I'm not a big proponent of memorizing these formulas, but I think if you do the proper practice with these, you'll have them pretty well memorized all on your own. Okay, so it's important to kind of recognize here when I have a plus minus that it remains the same for a plus minus over here. And all that really means is if I have the sum of two angles, then in the formula, it's going to be the sum. If I have this difference, then in the formula, it's going to be a difference. Whereas cosine, notice how it's different. If I have the sum of two angles, then in the formula, it's the difference. And if I have the difference of two angles, then it's in the formula, it's going to be the sum. And tangent kind of switches up. On the numerator, it's the same as inside the function, whereas the denominator, it's going to be the opposite side. Let's go and take a look at a basic example of why we would need the sum and difference formulas and how they could be helpful. So what if we had something like tangent of 5 pi over 12 and we had to evaluate it? Now notice that 5 pi over 12 is not on the unit circle. So this is not something that I am fully aware of. However, hopefully that you can agree, we can rewrite this as a tangent of 3 pi over 12 plus a 2 pi over 12. And we can definitely simplify that here to equal a tangent of, let's see, 3 pi over 12 can be reduced to a pi over 4, and a 2 pi over 12 can be reduced to a pi over 6. Now I want you to recognize that this is the sum of two angles for tangent. So now all I simply need to do is go ahead and plug them into the formula. So basically what I have here is the tangent of pi over 4, which is going to be my alpha, my first angle, and then that's going to be plus the tangent of pi over 6, and that's going to be divided by 1 minus, and then it's going to be the product of tangent of pi over 4 times the tangent of pi over 6. Okay, so now we need to make sure that we understand how to evaluate these based on the unit circle. So remember tangent of pi over 4, well, that's just going to equal 1. And then tangent of pi over 6, remember what is that coordinate point? If you look on the unit circle, the coordinate point for pi over 6 is going to be a square root of 3 over 2, comma, 1/2. Now remember tangent is y over x, right? So 1/2 divided by square root of 3 over 2. Now, if you were to simplify this, what you'd get is a square root of 3 over 3. So that's something done in a previous chapter. So hopefully it's something that we are familiar with. Then in my denominator here, I'm going to have a 1 minus, now tangent of pi over 4 again is 1. And then tangent of pi over 6 is going to be again a square root of 3 over 3. Now what I can simplify this here is I can multiply the top and the bottom by 3, right? That's going to get rid of my fractions. And what I'd want to do here is just go ahead and simplify this. So just applying some distributive property here. What I'm going to do is I'm going to get 3 plus the square root of 3 all over a 3 minus the square root of 3. Now again, it all depends on what the answer is. Like if you have your answer as fractions, like that can be done. If your teacher tells to simplify and to rationalize the denominator, then you're going to want to make sure you multiply by the conjugate. So the conjugate in this case is going to be a 3 plus the square root of 3, right? Again, if you remember, this is exactly what we did on our verifying our identities. And that's going to be 3 plus the square root of 3 over there. Working over here on the left-hand side, this is going to be a perfect square trinomial. So that's going to be a 9 plus 6 square root of 3 plus 3. All over, in this case, it's going to be a difference of two squares, which is going to be a 9 minus 3. Now I can just go ahead and simplify things. 9 plus 3 is going to be a 12 plus 6 square root of 3. And then therefore that's going to be 6. Now I can divide that 6 into the 12, which is going to be a 2, and then plus a square root of 3. And there you go. Now that's going to be the exact value of tangent of 5 pi over 12. Now in this example, what we want to do is actually verify. We want to show that the left-hand side is equal to the right-hand side. If you're thinking about your identities, it kind of looks like the cofunction identity, but if you look closely, it's not the cofunction identity. So the only thing I recognize I can do here is actually apply the sum formula for the cosine function, right? Because again, this follows, I have the sum of two angles. So by applying the formula that I have for this, I can rewrite this as a cosine of 3 pi over 2 times the cosine of theta, and that's going to be minus a sine of 3 pi over 2 times a sine of theta. And again, we want this to equal a sine of theta on the right-hand side. Now, it's important to recognize where's this angle on the unit circle? What coordinate point does this represent? So remember, 3 pi over 2 here is going to be all the way down there. And that gives us a coordinate point here of 0, comma, negative 1. That's very important because the cosine of 3 pi over 2 is going to be a 0. Now, again, you could write this out, but I'm just going to do this each and every one. So therefore, this is going to be negative minus a negative 1 times a sine of theta. Well, 0 times cosine is just going to be 0. Negative times a negative is just going to be positive. So therefore, you can see a sine of theta is now equal to a sine of theta on the right-hand side. So whenever you see that sum or difference of two angles, you know you can apply the sum and difference formulas. Now, in this next example, we're given actually some triangles. And a lot of times what's common is actually give some expressions where you'd have to actually create your own triangles. But that's something, again, that we did in a previous chapter. So hopefully it's something that you can create on your own. In this example, we're given the two triangles. So if we want to evaluate the sine of the difference of two angles, well, we have the triangles. We're just going to look at those ratios that we have for our angle U and angle V. So if I have sine of U minus V, again, just write out the formula based on the difference of these two angles. So that's going to be sine of U times the cosine of V minus a cosine of U times a sine of V. Now I'm just going to look at each triangle. And again, this is all relative to our angle and just apply my ratios that I have. So the sine of U, remember that's opposite over hypotenuse. So that's going to be a 4/5. A cosine of V, remember that's adjacent over hypotenuse. So that's going to be a 5/13. And then cosine of U, adjacent over hypotenuse, that's going to be minus a 3/5. And then a sine of V, which is going to be 12/13. Now I can just go ahead and simplify this out. So 4 times 5 is going to equal a 20. So 5 times 13 is going to equal a 65. And then minus a 3 times 12 is going to be 24. That's going to be a 36. All over, again, another 65. Now 20 minus 36 is going to equal a negative 16. So I'll have a negative 16 all over 65. So just to recap, whenever you see the sum or difference of two angles, look to go ahead and apply these identities and practice them because we use them a lot in different applications. As you can see, I did a different style of problem for each one of these. Last topic I want to cover is going to be the double and the half angle formulas. Now, very much like the sum and difference formulas, these are formulas that are very important. When you see a double or a half angle, you should know these formulas, but I don't think it's a good idea just to try to memorize these. I think it's the best idea is to practice these over and over. Therefore, you feel like you have a solid understanding of how to use them and how they are different from one another. So I know you might be looking at these and be like, whoa, that was a lot. And there's no way I'm going to memorize these. And yes, I can definitely agree that even when you have multiple variations of some and they look kind of confusing, they can definitely be hard to remember. But again, if you go through practicing problems over and over, each and every year I would forget these. But then every single time that I went back through the material and I practiced these over and over, I had these memorized to a T. So you can definitely do it. Just please focus on practicing these rather than just trying to memorize the formula. In this first example, what I'm going to do is look into solving this. So whenever you see the double angle formula, which in this case we have a 2 theta, then you're going to want to apply the double angle formula. Right? And you can see that sine of 2 theta can be rewritten as a 2 sine of theta times a cosine of theta. So what I'm going to simply do here is I'm just going to rewrite this as a 2 sine of theta cosine of theta minus a sine of theta equals 0. Now what I recognize is I can factor out my 2 sine of theta. This is exactly the same process we did earlier in this video. So by factoring out a sine of theta, now I'm left with a 2 cosine of theta minus 1 is equal to 0. Now I have the product equal to 0. So therefore I can set them both equal to 0. So I have a sine of theta equals 0. And I have a 2 cosine minus 1 is equal to 0, which you add the 1 divided by 2, I get a cosine of theta is equal to a positive 1/2. Now, if we're only looking on the interval of 0 to 2 pi, all I'm going to do is then just look at, well, on the unit circle, when is sine of theta, which is the y coordinate, equal to 0? Well, that's going to be at 0 here. Let's go and use an interval notation. So that's going to be at 0 as well as at pi, right? Because this coordinate point here is a 1, 0, and this coordinate point is a negative 1, 0, right? When is cosine equal to 1/2? Well, again, that's going to be that point and that point, which if you remember this angle was pi over 3, and that angle is 5 pi over 3. So I'll just add these two angles. So pi over 3 and a 5 pi over 3. So in this example, sine was pretty easy, right? Because there's only one option. Now, when you're dealing with the double angle for cosine, again, sometimes it gets a little tricky, but again, pick whatever you need to. When you have sines and cosines squared, it's probably best to use this top equation. When you're trying to have the expression only in terms of cosines, use this one. If you want to have things in terms of sines, use that one. So it all really depends on the problem, but a lot of times we can use the double angle formula for solving as well as for verifying identities and evaluating functions. Now, let's take an example. I have the cosine of 15 degrees. Now, you could definitely use the sum and difference formulas, right? I could rewrite 15 degrees as 45 minus 30. But obviously, in this example, what I want to do is practice using the half angle formula. So the half angle formula says if I have cosine of an angle divided by 2, that's going to equal plus or minus the square root of 1 plus cosine of alpha divided by 2. So the important thing you need to understand here, if I have alpha divided by 2 is equal to 15 degrees, right? If I'm saying this is alpha divided by 2, well, then what's alpha? Well, multiply by 2 on both sides and you'll get 30 degrees. So therefore, using the half angle formula, I have this plus or minus square root 1 plus the cosine of double this, which is alpha here, which is 30 degrees, all divided by 2. Now, a lot of students will get confused with this plus or minus. And basically all this is telling us is what angle is my half angle in? Is that going to be cosine is going to be positive or negative? So if you think about this, if you look at this half angle, which is 15 degrees, that is in the first quadrant, right? So therefore this answer, whatever 15 degrees is, let's say, if that's 15 degrees, we know we're going to have a positive answer. So therefore, rather than using the plus or minus, I'm just going to include the positive answer because there is no negative answer for 15 degrees. So now let's go ahead and simplify this. So we have only the positive version. So cosine of 30 degrees, let's say like that's 30 degrees. We know that's going to be square root of 3 over 2. So it'll be plus a square root of 3 over 2 divided by 2. So now we need to go ahead and simplify this. So under the radical, I can multiply by a 2 over a 2. Now again, make sure you're applying distributive property here. And what you'll get here is a 2 plus the square root of 3 all over 4, which now I can rewrite that as a 2 plus the square root of 3 all over the square root of 4, which that's just going to simplify down to a 2. So therefore I can rewrite that in front. So 1/2 times 2 plus the square root of 3. All right, in this last example, what I'm going to do is use actually an example of the double angle formula as well as the half angle formula if we're given a triangle. Or a lot of times we might be given an expression where we'd have to create our own triangle. But again, we're just going to apply the identities here. So if I have the cosine formula, I'm going to pick one of these. Now again, it doesn't really matter which one you want to pick. When I'm usually evaluating, I typically like to use the cosine squared minus sine squared to go ahead and evaluate my expression. So if I have the cosine squared of, this case, 2u is going to equal the cosine of u minus the sine squared of u. Now I just look at my triangle and say, what's the cosine? Well, cosine is adjacent over hypotenuse. So that's going to be a 3/5 squared minus the sine, which is going to be a 4/5 squared. So 3/5 squared is going to be what? A 9 over 25 minus a 16 over 25. 9 minus 16 is going to equal a negative 7 over 25. Now in this example, I have the tangent of u divided by 2. So again, I want to go back over these expressions. Now, which one should you choose? I typically like to choose the one where I have just one function in my denominator. So that's going to be a 1 minus cosine of alpha divided by a sine of alpha. Now, obviously in this example, we're using a u, so that's okay, but we'll go ahead and rewrite this as a 1 minus a cosine of u divided by a sine of u. So now we just look at this and we say cosine of u, again, that's 1 minus a 3/5 all over a sine, which is going to be a 4/5. Now there's a couple different ways you can go ahead and do this. I don't like having this 4/5 in the fraction, so I'm going to multiply by the reciprocal on the top as well as on the bottom. So when we go ahead and do this, I get a 5/4 minus a 15 over 20. Then to get common denominators, I will just multiply by a 5 over 5. What that gives me is a 25 over 20 minus a 15 over 20. And that can simplify over to a 10 over 20, which just simplifies over to a 1/2. So there you go, ladies and gentlemen. Hopefully that is a decent cram session for identities, helping you be able to simplify, verify, solve, apply the sum and difference, as well as apply the double and the half angle. I hope this video was helpful for you. If you want more individual quick examples, then go ahead and check out the reference material and examples I have down below, or check out the next video I have for you here. Cheers.